Good morning. Welcome back to EELE 461, 561 Digital Systems Design. This lecture is associated with our Monday meeting, which would have occurred on April 20th. And so what we're going to do in this video is start looking at differential signaling. Now, this ties in very heavily with what we have been looking at over the past week, which is this whole notion of coupled lines. And up until now, we've looked at coupled lines as basically kind of a nuisance, right? I mean, you have a 1 or a 0 you're trying to transmit to a receiver, and somebody else, some other trace, gets too close to you, and all of a sudden it alters your impedance. And so the trace that got next to you, it was a victim in the sense that you coupled some of your energy onto it, but it was also a nuisance because it changed the impedance of your own line. So it actually caused reflections on you just because it came too close. And then what made it even weirder is that the reflections that were caused, or the way that it changed the impedance of your line, varied depending on whether that neighbor was transitioning up, transitioning down, or was held at 0. And so it made it really difficult to terminate anything because your impedance was changing. So we did not look at that in vain. There was a reason that we went through all that derivation for Z odd and Z even, because ultimately we are going to use all that. It'll all come back when we start thinking about this new type of signaling, which is called differential signaling. I will tell you right now, when a neighbor comes along and gets too close to you, it can cause your impedance. If it's held at 0, it causes your impedance to change. And the solution to that, when you run what we call single-ended, which is where you're just sending one line per one bit of information, the solution is just to space your neighbor out. So don't put traces too close together. We are now going into a situation where we are going to actually use 2 pieces of conductor to transfer one logic level, okay? So this is called differential signaling. And here's the way that you can think of it schematically. You are going to have a transmitter, and it is going to take a logic value. It's going to essentially encode it into 2 signals that are complementary of each other, and it is going to send it down to a receiver, and this receiver is a differential amplifier, okay? And it will perform A minus B, just like any amplifier does, okay? Any op amp, any amplifier you've ever done, it just subtracts these 2. And what happens is that if you look at A, which I write right here as blue, A will be considered the regular signal. So if you just look at this by itself, it's 0, 1, 0, 1. B is going to be the complement, and so it will always be the opposite logic level. And when you do that, if you subtract A minus B, you will get a signal that tracks the logic kind of value of A. Now you might ask, why in the world would I do this? I mean, it seems like a waste because I'm getting basically the waveform back that A was. Well, it turns out there's a lot of advantages to doing this. But I will say, first and foremost, you have to have a differential receiver. If you don't have a differential receiver, all you're doing is sending 2 logic values down here, and it's a waste because you have single-ended receivers right here. It doesn't help you at all. So you got to have a differential receiver. And these exist. These are all over the place. Once you start learning about differential signaling, you'll notice that it's everywhere. Okay. So what are some advantages? First, the first advantage is called this thing called common mode rejection. Common, we're now going to start introducing some new terms. So common is quite easy to understand. It's something that's common to both A and B. But mode was the way that we stimulate it. So if you had a common mode, what that means is basically you have a blip or noise on both signals. And what would happen if you had that? So let's say that something happened, like a radiation strike blasted through your board and caused this, or some EM coupling came from some external source. So you had some power supply wackiness, and all of a sudden a blip was put on there. Well, if you were single-ended, look at A, you might actually get high enough on this piece of noise that it would trigger a flip on the receiver. But if you do A minus B, the blips are gone. So as long as they're the same on both A and B, they will be removed. or what we say is rejected. So this is called common mode rejection. And it just is a fancy term for that. If you have any common signal on both, it will subtract them out. And we'll come back to that in a second. It's kind of interesting, but it's basically, it subtracts out noise. Noise. Another thing is that when you use a differential amplifier as opposed to like a digital logic receiver, which think about our digital receiver as basically an inverter, when you're transitioning between a 0 and a 1, it does its best job possible to try to figure out whether a 0 or 1. But when it goes through the middle region, it kind of goes into no man's land. So it doesn't know what you are. So that's why you have to hammer through it so fast on a single-ended signal. When you have a differential amplifier, one of the things that happens is that it subtracts these two. And the signal that it produces is going to actually have twice the voltage of the incoming signals. And it's doing a true subtraction throughout the entire transition. And so if you think about this, let's take a look at a signal that, let's say you had like a 2-volt DC offset on both signals, A and B, and you swung from 1.95 to 2.05 with A, so you're only swinging 100 millivolts peak to peak. And B went, was the exact opposite of that. You have 100 millivolt peak to peak difference. When you do the subtraction, it's basically going to go A minus B, but it's relative to this offset. And so what you end up getting is you basically get like 1.05 minus 1.95 is 100. That's 100 difference there, but then you switch it the other way, and it's essentially negative 100. So you get 100 minus negative 100. So the ultimate output of the differential amplifier is 200 millivolts. And that means that you get twice the voltage. So due to the doubling of the actual output of the amplifier, and due to the fact that you're doing a true A minus B throughout the entire transition, differential signal amplitudes don't have to be as big as single-ended amplitudes. So for example, if you have a CMOS chip, you're looking at like an MCU, so like an MSP430 or something, and you're running just regular output CMOS levels. Your outputs are swinging from like 0 to 3.4. That's a huge signal swing. There's a lot of power to generate that. When you look at differential signals, so stuff that's like in USB or standards like low voltage differential signaling, LVDS, or even what's in like your computer, PCI Express, serial ATA, any of these differential interfaces, the signal swings are really small. So they are like measured in the 100 millivolt range. Think about that compared to what we're used to as single-ended signalers. We talk CMOS levels. We're like, well, I have a 3.4 CMOS standard. That means I go from 0 to 3.4. That's way bigger than doing 100 millivolts. Or even if you go down to like, I'm a 2.5 CMOS or 1.5 CMOS, 1.8 CMOS. Those are big signals compared to what you're able to signal with when you do differential signaling. And again, it has to do with not only are you doubling the output of the amplifier because of the A minus B, but the A minus B does a true subtraction of these two signals all throughout the transition. It's not a single-ended receiver where it's like it doesn't know what the voltage is right in the middle. Okay, so we kind of say high receiver gain, but that's what it is. You get to use smaller signals to produce the same logic level transmission. Okay. You also have less simultaneous switching noise. So remember, simultaneous switching noise was where the most common one was where you had a whole bunch of signals that were sharing a common return. Well, in differential signaling, you always have a signal going in, current going out that corresponds to the signal and its complement. So you actually inherently always produce your own return current. So you never even have to use the ground of your IC. You're always returning back and forth through yourself. Finally, it's good for low-cost cables. So if you have a really cheapo cable, like a twisted pair cable where it's just like you just take two cheap wires and you twist them together, you're able to reject a lot of noise that can be coupled onto the cheapo cables. And when I say cheap typically means you're not shielded. Coax cable would be what we call an expensive cable because you have an outer ground around your signal. And that's like we call it expensive relative. Cheap cables are just a wire. And so if you have a cheap cable, you need to do something because you can couple onto that like crazy. So what if you use two cheap cables and twisted them? and then did differential signaling, you would be able to reject noise that's coupled on commonly to both conductors. What's the disadvantage? Well, number one, you got to have twice as much copper, right? So if you need 2 traces on a printed circuit board to send 1 logic level, 1 bit. You need 2 pins on a device to send 1 bit, okay? But you see this all over the place. Once you know about it, you'll see it everywhere. Okay, let's define a couple voltages. We're gonna have differential voltages and common voltages. So differential and common signals, okay? Think about your differential as it's the voltage between what we call the P, or the positive trace, and the N trace, which is the negative trace. So the voltage wave that represents a signal, it's between trace 1 and true. It's between P and N. And that's V diff is V1 minus V2. And these are switching complementary, and they're always designed like that. You never have a situation where this one's still going and N decided to go to 0. They're always complementary of each other. So that's where you think about the differential voltage. That's how you transmit the wave, not to the ground. Now, that's not to say that there isn't also a voltage that exists to the ground, because you do. You have a common voltage that is basically the same voltage on both traces. And that is, you can think of it as the traces to ground. Now, why is it common to both? It's like, well, we talked about the noise, but really what it is, mainly it's the DC offset. So you're not going to have signals that are centered around 0 volts. You're going to have them centered around something like 2 volts or 1.5 volts. And so you're going to have a common DC offset to both of these. But what's interesting is that when you do the A minus B, it's going to subtract it out. And so you get rid of that DC offset at the output of the receiver anyway. But this is the beauty that allows you to also remove any common noise that's on there, okay? So when I say common, it can be a 2 volt DC offset on both, but it can also be a little blip that happens on both of them, okay? And you can kind of define common as 1/2 V1 plus V2. And that's just, kind of simple math of how you do it. But anyway, that's the other type of signaling. Okay. So now if I tried to define my entire thing, you could call the P side, which would be A in this situation, V common plus 1/2 V diff, and then V2 would be V common minus 1/2 V diff. And if you look at this, it's really simple. It's basically, in this example, V common would be 2 volts, which is the DC offset. V diff would be the difference between these two, which ends up being twice the peak to peak of the individual signals, or 200 millivolts. Okay, so those are just kind of the signals. All right, how are these implemented? This sounds like impossible, right? Well, it's not that bad. Edge coupled microstrip. Just use 2 traces on a printed circuit board. Edge coupled strip line. Go ahead and use two printed circuit boards on the same layer on a printed circuit board. It's not that hard to implement. Broadside coupled strip line. This is what we're actually doing in line calc. Line calc I can't find the one for edge coupled strip line, so we're always using this broadside coupled, but it basically just means they're vertically on top of each other. So if this was layer 2 and this was layer 5, this would be layer 3 and 4, and the coupling between these is right there. And this is actually a really strongly coupled differential pair. It's a really good one. Coplanar just means you have 2 traces that are so far away from any return plane that they cannot return anywhere else other than through themselves. Not that you would anyway. Twisted pair, if you took a pair of scissors and cut open a USB 1 cable, you just see 2 wires in there. That's P and N. But then there's this monstrously expensive cable, which is called a twin ax. This is what USB-C cables are, or USB 3. Have you ever held a USB 3 cable? It's heavy, it's expensive, and it's because you have a P and an N conductor, but it's also has a shield around it like a coax, and they call that a twin ax. So those are the basic implementations that we see, okay, of the interconnect. All right, that is it. So that's kind of the basics of differential signaling, some terminology, and then some implementations that are common amongst the interconnect. All right, that's it for now, and we'll see you.